So good afternoon, everyone. And my name is Chin, and I'm the founder of CEO of Zettar. Young already made the introduction, so no more. And so today, the subject of the talk is data movement at speed and scale as the fourth IT pillar. And what are the other three? The familiar storage, computing, and networking. The talk is also a story of a relentless pursuit of a ever higher data transfer rates year after year since 2015. And then furthermore, how two Samsung's new products, can play a significant role in this story. And I invite you and the audience watching this remotely, ask me questions anytime. Don't worry about interrupting the talk. And all my slides have the external online references linked in live, okay? So if you're curious about anything, raise your hand. I'm happy to pull up the references for you and you can take notes. Having said that, let's start the story. Give me just a second. So why the data movement at the scale and the speed has to become a fourth IT pillar? There's a reason for that. It's simply because the world faces exponential data growth. People in this room and the remote audience know about this very well. So this is a cliche. But even though it might be a cliche, the famous British physicist Lord Kelvin said one time, he opinioned, if you do a measurement and you can put a number on the measurement, you understand what you measured to some extent. So luckily, when you tell people the world faces exponential data growth, luckily with Navin Shenoy, he is the executive VP of Intel's data center group. He already revealed last year two very incredible observations. And the first one is 90% of the data, world's data, was generated in the past 2 years. From his timeline, that's 2016. The next one is even more stunning. He said about only 1% of such data is utilized, processed, and acted upon. Now, he said this, by the way, at the Intel Innovation Summit in August 2018. Now, why such a poor data utilization? Even though we consider we are in a digital age and data is currency of the business, it's so important. Everybody is trying to be doing a data-driven business decision making and all that. In our opinion, humble opinion, the simple reason is data movement at the speed and scale is too difficult. The culprit is the incumbent data movement solutions, hardware and software. They are all designed a long time ago, some even more than 2 decades ago. They were designed not to be effective in tackling the exponential data growth. When you design something, let me just give you a simple example. To design a small family car for commuting is one thing. To design a high-performance Formula One race car, that's another thing. So you want to enter a family car into Formula One racing, the chance of winning is probably nil. So I also, from our intense experience since 2015, we come to this conclusion that in order to solve your data movement problems, it's very, very fruitful to know the different types of data movement solutions and which situation to apply them. So this is an important slide. I'm sharing this with you with the intention to convey what we learned the hard way. So there are 3 types. The data access solution, they apply to the the problem sets fitting the three characteristics down below. Mainly the data transported in small amounts, okay? And the rest you can glance yourself. The second one, data transport solution. This one is the most difficult and challenging one, and as the story moves along, you will see why, okay? The most applicable or most distinguishing characteristic is that it deals with coupled data flows. That is, you might have multiple data flow or single one, but if you have a multiple, they are related, correlated to each other. They are not independent. I will mention some example. I gave 2 examples there. It's linked to online paper. If you're curious later on, just raise your hands and tell me, I can pull them up. And I think the Wi-Fi works here pretty well. And the third one is data traffic aggregation solution. This one deals with independent data flows. You have multiple data flows, and they are not correlated to each other. Then you can use this. And the best example I like to cite is the 2013 Comcast example. Comcast in 2013 in the East Coast between 2 major metropolitan areas, Chicago and New York, already faced more than 1.4 terabits per second data rate. So what Comcast ended up doing is it came up 15 times 100G aggregation backbone link, okay, connecting the 2 metropolitans in order to handle this high rate. And there are others. Google, between 2011 and 2013, came up with a B4 traffic management system. It's a software-defined WAN, okay? In order to make the utilization of all the connections linking global data, Google data centers, achieving utilization rate almost like more than 95% all the time. And then ESNet also in 2015 had very nifty 2 times 200. Back in 2015, that's very novel, okay? And in order to migrate the data center from NERSC, the Supercomputing Center, from Oakland to Berkeley Hills. And Shell, in last year, starting from last year, I believe, had like 8 times 100G connections between the 2 data centers. And then to do replication up to more than 7 petabyte per day, okay? And then you go to SC18 or SC17 website, you go to the network research category, you will see. So this is, to put it short, this is a very well-established category with a very well-known methodology to accomplish. But you can see everything I mentioned involves some kind of a custom solutions or the use of the SD-WAN techniques. And there are many examples, but the complexity and the management of this type of solution is quite significant. The second one is very difficult. The reason is because usually, hold on, because it involved all the 4 stacks: storage, computing, networking, and the software stack together. So you have to do a holistic and integrated consideration of all the 4. It's not that easy, okay? And so, but that's becoming more and more dominant, and that's what we are focused on. So for that data transport category, can you visualize it? Yes. And Yang said that the hyperscale distribution is a mouthful, but if you describe everything here one by one, that's even more mouthful. So we just came up with an abbreviation called hyperscale distribution. What is hyperscale data? It's defined on the left side of the slide. And so you can see the data size goes up from terabyte to all the way to zettabyte. And you also have to consider file and object size, because not everybody is using files. Some use object. It can be from kilobytes to terabytes. This is what we have seen in real life among our customers. A number of files can be from a few, and to, like for the LCLS project, to hundreds of millions when we were doing a mail server farm migration, tech refresh migration at the hyperscaler, okay? It's per volume, even per bucket. And typically, now talking about moving the data, typically there are two upper popular methods and everything in between. You can have hardware shipping like Amazon Snowball. You can also over high bandwidth. But if you use the hardware shipping, even Amazon itself, it announced 1 petabyte per week. That's the upper bound. And for the typical over high bandwidth transport, that's also 1 petabyte per week. This is the published results. Like I said, I have everything lively linked to even government publications. So if you raise your hands, I can call them up. And then you need to move them to cloud and to data center or between the two. Now, most of the time, not usually, most of the time, we deal with this case. So can you visualize it? Yes, we can. So I like to use the water transport analogy. We are living in California, so we are lucky. We know Bay Area, the water is supplied by the Yosemite Hachi Hachi Reservoir. So what are the 4 elements of such a large-scale data transport system? In order to make it successful, there are 4 of them. First of all, you need to have a reservoir with water, and we all remember that the past few years, the California in drought, not pleasant. The next one is if you go to Hillsboro, you go to the water temple, you will see multiple pumps. Why? Redundancy and the high volume just requires a cluster of pumps. Then you need electricity, that's granted. And then multiple pipes. Again, you go to the water temple, you will see 2 large pipes running down the hill. For high-speed over-the-network data transport, it's almost exactly the same. Maybe I should change the Intel logo to Samsung. But anyhow, SSDs are good, okay? And then you have to have the digital water pump. That's a software. Now, how about servers? Server provides, they drive applications, so they are like a utility. And then the 100G connections, current state of the art, is like a counterpart of pipes. The most important thing here is just when you build a water transport system, you have to design the 4 elements together. It's similar for transport system. In a DOE Exascale initiative, this is called co-design concept. And then, of course, just like for the water transport system, the infrastructure side, before you run the software, has to be made ready first. Now, you may wonder, who has or faces this kind of large transport issues? I give you some sample industries. Not only we have been paying attention since 2014, but also a few that we have direct customers in it. They are all tier 1s. So these 4 are what we have our customers, okay? I mentioned, casually mentioned a few. They interacting with so many customers in different industries really helped our software's design, evolution, and progress. But this big science project called LCLS-II, meaning Linac, Coherent, light source, laser, second stage, is the biggest one that drives the design and the enhancement of the capability of our software. This is a very, very incredible project. It's a world-class discovery machine. Why? It generates strobe-like pulses that's, listen to this, a few millionths of a billionth second long. That's how short it is, but it's a billion times brighter than any laser light so far obtainable in the world. As a result, it can make some really penetrating investigations to new materials, for instance, that so far just not possible with other methods. So this one is driving our software's advance most, and we also do a lot of effort every year in order to meet its requirements. Now, what are the job requirements? I happen to have the pleasure of Dr. Les Cottrell here. Les, could you please wave your hands? Yeah, he in 2016 drew up this and gave it to me. Chin, this is your job requirements. I said, okay, sir. Now, what are the job requirements? Let me just make a few things clear. First of all, have you noticed starting from this year, it gets into exponential growth stage. Every year, we have to double the transfer rate. Then, secondly, eventually by 2024, it has to exceed more than 1 terabits per second transfer rate, and that's coupled the data flow. It's not aggregated. The tens, let's go back to this, and so you will see. So tens of thousands of laser detectors along the 3 miles long laser, they spit out data, but they are all spitting out data for a single experiment during a period, like 2 weeks long generally. The data flows are correlated. You cannot treat them as independent. So it's a data transport problem. You cannot aggregate it. Now, what we have done are 2 stages. First of all, we need to prove that the software architecture is good enough for really high-speed transfer. And then secondly, it can really handle 2 large file transfers. So between 2014 and 2016, we were evaluating the architecture. So we, right before Supercomputing 2016, we proved that the architecture could achieve 200 Gbps. Then starting from 2017, we began the evaluation of 2 large file transfer. We were limited, like Yang said, 80 Gbps because the connection is a production link. We have to share the traffic. But from then on, in May 2017, we proved that it could transfer petabyte in 34 hours. Just check on the internet, you will see it, including government publications. We don't make claims. Then last year, we said, gee, that's not good enough. Let's see if we can do better. So we spent about a whole year improving the concurrency of the software. And then also with new Optane SSDs, we were able to achieve 1 petabyte in 29 hours. So in 1 year, 15% improvement. And I usually, as an engineer, I don't like to review what we haven't done, but this time I'm tempted. So I will just tell you, give you something. So this year, we like to prove we can do 1 petabyte in 14 hours over 2 times 100 G connections, which Slack already has. That's our job requirements. Now, you may say, let me just say this. In this talk, since it's going to be a story like a talk, I will not get into very low details during the talk, so I'll just mention everything at high level. So this one addresses possibly the question, what kind of software architecture you conceive in order to handle such exponential data growth? The one we came up is a peer-to-peer cluster design. Okay, so why peer-to-peer? Because it makes running cluster almost as straightforward as running a single node. Why in high-performance computing, only in computing jobs you need to consider cluster? Why not transfer? Especially transfer rate is exponentially growing. You have to use a cluster to handle it. It's just a simple logic to us. So we decided to this. But then we look at the cluster formation in HPC. They typically use very rigid software framework. We didn't like it. And my founding principal engineer and I happen to have good background in peer-to-peer. So we say, let's go with this. So we did it. And it has proven to be a right decision. Sometimes, creating software is not a matter of science. It's a matter of luck. It's a matter of art. It's not a true engineering. So, but let's get back to the story. So what's the advantage of this? One, managing a cluster of nodes, you can use any peer as the management entry point because they all know each other. That's why they are called peers. Secondly, there are some surprisingly delightful benefits. For instance, I list 6, but I won't go through all 6. And because they are peers, so the high availability is not just at the node level, like a typical cluster. You can handle network interfaces, multiple network interfaces, node level, even connections. Like I said a while ago, Slack has 2 times 100G connections. They are independent connections. And the software is able to deal with 2 independent connections at the same time. So also because they are peer-to-peer, so you no longer need to handle the cluster using a cluster workload manager like a Slum, Torque, or IBM platform. They can coordinate among themselves. Say node A is busy, node BCD will say, you take care, okay, we will take over yours. They can do that. So let's keep going. Now, everything we do, especially for the LCLS project, is available, public, worldwide visible on this network overview portal offered by ESNet called my.es.net. So this is occasionally what I will do. See, you can do it anytime. I don't think the Samsung firewall blocks it. So you can go to this, and then I will close the browser now since it takes too long. But the key point is, when we do the pre-production trial runs, there are many people in the lab and in ESNet watching. And so whatever we report, I mean, they have to be factual. And this is something you might want to take a look. See this wiggle here? And occasional wiggle here? Because this is a pre-production trial run. So we have to share the bandwidth together with other production traffic. So sometimes our software just have to back off. And but the key thing is the software has to have the ability to recover fast. And that's the important thing for production use. It's not a lab experiment. Oh, ideal network, full 100 for several days. You can't do that. Now, Yang mentioned that we competed early this year in this international competition called Supercomputing Asia 2019 Data Mover Challenge. What motivated us is actually not just the competition, because as a business, we have many other things to do, customers to take care of. What motivated me especially, and my team also, is the opportunity to really test out our hypothesis obtained since 2015. In order to get back to this, see this loop, 5,000-mile loop, is only 5,000 miles, owning 5,000 miles. Over the years, we have shown that using TCP in an appropriate way, the latency, network latency doesn't matter. Now, when we saw this, we say, whoa, this is excellent. You know why? Because from Singapore to Kisti in Korea, the distance is 17,000 miles or 27 kilometers long, and latency is more than 400. Over the 5,000-mile loop, the most we got is like around 120 milliseconds. That 400 is satellite level. And my team and I just say, yeah, let's go for it. Let's see, really prove and that the software works even for this kind of long latency, long haul network. It's all 100G. So we did it, and luckily we won. So that's the end of it. So now working in a different industry happens to have one advantage. That is, the software is not just tailored for one particular set of requirements. For instance, the software, even though as a transfer software, it can do something nifty that typically only replication software can do. That is, it can compare the difference of 2 different data sets and just transfers the delta. And that's the first one shows it's a snapshot, full snapshot transfer first. And then the second one is just the difference of the 2 snapshots. And furthermore, it supports data distribution pattern, which can be very useful, especially to distributed companies such as Samsung, for instance. You can use it inside of data center in a LAN environment. You can transfer from that data center to data center. You can transfer from data center to maybe a public cloud services or another private cloud services somewhere in your company. and you can handle. This one is particularly useful to, say, media entertainment industry. The central one could be a major studio like a NBC or Fox. The rest are post-production workshops. And this one typically is very well known in the high-end physics, high-energy physics collaboration. The root could be, say, like a CERN in Switzerland. The rest could be various different national labs. And then the third level most likely are universities. Now we are talking about patterns. I'd like to bring it out to you. As an engineer, it really pays to figure out the patterns of your problem. Then you can, very quickly, you decide which solution can be tackled with, which set of the problem can be tackled with certain solutions, okay? So now I will start talking about another set of patterns. This is a more visual, graphical representation of the hybrid storage cloud pattern in a large distributed enterprise. And as you can see that you need to use a POSIX file system for scratch file system, but keeping majority of warm and cold data in object storage. But the tool has to be able to transparently move data back and forth. And then you need to be able to move the data from either one to another facility, okay, or to a public cloud, either to the compute instances or to the object storage directly, such as S3, such as EC2, okay? So this is pattern. But you know what? There is an easier way to talk about data movement patterns, which is what I'd like to show you next. It's called drainage basin pattern. And everyone here has taken some geology classes. You should know about this famous pattern. Or river system, if we are living in the Bay Area. So Sacramento River and the upstream follows this drainage basin pattern, okay? And this pattern actually is how you ought to think about many seemingly diverse disciplines. I mentioned just a few, like autonomous cars. In Samsung, that's ADSD, okay? And then IoT, well, Samsung Mobile definitely falls in that. And the interesting thing is they all need to use edge computing, which I'm gonna talk about next. And by the way, edge computing is something that even large science projects like the LCLS-II I mentioned before will need to use sooner or later. And another stunning example, if I have time, I will discuss about it. It's called square kilometer array. So what I like to explain with this slide is that the edge and hybrid cloud computing usually are close correlated. And why? On the right-hand side, you see the typical Internet of Things, okay? I didn't say pull out the autonomous cars as a separate category now. I just lump them all into IoT. Typically, they have to do some edge processing first, say using FPGAs inside of a car, for instance, and then the data will be aggregated into the local aggregation location, okay? That's where you do the so-called more data reduction, for instance. That's typically done with servers. And FPGAs, you see I have two connections here. It's because servers may also use FPGAs as well. And then depending on the eventual needs, the resulting data may go to an enterprise private cloud data center, or they may go to a hyperscaler data center. And the two, even the enterprise, like the showed previously, they may even communicate and move data back and forth. So they are all closely related. It's a very unfeasible, in my humble opinion, at current stage, to eliminate all those intermediate steps. Because if the Mother Nature tells you, hey, this is how a drainage pattern looks like, you always go from upstream to fork to the major river, we human beings better follow the Mother Nature's examples. So I'm going to wrap up everything I have talked so far with by explaining quickly the DOE Exascale Computing Initiative's co-design concept. Co-design basically says integrating storage, computing, networking and the software into a holistic consideration for the optimum. I didn't say best, optimum, because you can have multiple optima. Some could be local, some could be global. Nobody can be so arrogant and say an approach always gets you the best result. We can say optimum. So for optimum results. So that's why along a data path, in the context of data movement, you start with storage, you then get into compute or servers, which runs software, and then get into the network connections outside. So always 4 elements, you have to consider them at the same time. And of the 4, the storage throughput is always most important. It's not network, because network in large enterprises, 100G is common commodity. And I will just say this. I went to Bio IT just 2 weeks ago, and the CTO of a local company, large service provider called Markley Group, he told me that his company has a financial client which wanted them to offer a connection, and that is a bundle of, listen to this, 48 times 100, that's 4.8 terabits per second. It's a financial institution running the connection from London to Boston. So you can see that the point is, large bandwidth, network bandwidth availability is no longer an issue in today's world. It's the storage, and Young can attest this, okay? A best SSD created by Samsung can only go so fast. You have to aggregate them. How to do that is still presenting a challenge. Now, I want to mention something. When you do data transport, eventually there is one issue you will run into. That is this dilemma. Most of the storage pool are designed for capacity today, not for throughput. So how can you get high throughput? And before you can get high throughput, how can you claim that you can fill the rest data paths with the data? You can't. Logically, it won't happen. I mean, data won't grow from the thin air, okay? So tiering becomes a proven solution, but the typical tiering is for caching, that is data reuse. And here you may see this. We keep talking about high data transfer rate. So if you're a storage, the tiered storage is small, then you can the transfer will a quick blast and short. Then you wait. That's why the people are waiting impatiently. And then another, once it's filled up again, another short blast, and another wait. This is no good, okay? So what you need to do is to make a HPC specific tiering, and it becomes interleaf. How can you do the interleaf? That's what I'm gonna explain a possibility next, again with the Samsung's products, okay? With HPC tiering, what you can achieve is a smooth, consistent, high utilization. How can you do this? Samsung products, 2 Samsung products can help. What are they? The first one is the Mission Peak series of storage servers. They are compact, they are ultra high density, and 1 petabyte, and as Samsung ramps up the capacity of the NF1 SSDs will be even bigger. That's something you can leverage for compact form factor, but the ultra high density. Then you can interleave between the 2 servers and achieve the high utilization. And I was talking about in the previous slide. And then this NF1 form factor is compact. But the good thing is here, Ron, smile, it's your group now. The key value SSDs. That's true object storage. Very few people are aware of the fact that the so-called private object storage software sold out there, oftentimes they sit on top of a set of POSIX file system. So when they tell you you are using an object storage, actually you are not. You are just indirectly accessing POSIX storage. But the Ron's group and what his colleagues and his team worked on will make this a true reality. Ron, is that correct? And I think I'm at the end of my talk. I will just say you probably can detect a theme that I keep emphasizing small form factors, compact form factors, high densities, and all that. In fact, being in HPC space for a long time, I tend to honor the father of a supercomputer, Samuel Cray, saying very, very much. One famous quote he had was, as long as we can make them smaller, we can make them faster, okay? That's what NF1 is, that's what the mission peaks is, and that's exactly what reflects his wisdom, okay? And another thing is from the German-born British economist, Schumacher. Small is beautiful. I'm sure many of you have heard about that. So with that, I conclude my talk, and thank you very much. I hope the story is entertaining enough for you, and I welcome any questions or discussions.